So welcome to this meeting. So my name is Paul Dodds. I'm from University College London. I have the pleasure to be chairing this meeting, which is on high temporal and spatial resolution modeling using times models. And I'm very pleased we have a couple of great talks for this. One from Marcus Lesel first from IER, and then secondly from Tom Kober and from Evangelos Panos at PSI, who are both going to be talking. And they're all going to be talking about their experiences. We'll take some questions after each talk, and we'll also invite more general comments and kind of hints and tips about how other people approach high resolution modeling. But first of all, let's start off with Marcus. Over to you, Marcus.
So thank you very much for your introduction. I want to tell you something about local energy systems or high temporal modeling. I want to start with a little bit of background, then a little mixed going to simulation of prosumers, and then saying something about time resolution in such a model. So in general, yes, if you are using times local or this local energy system models, the target is to analyze also the low cost greenhouse gas neutral energy system till 2050. Yes, looking what will be the requirements related, for example, energy and transport systems, what is the influence of charging in the network and so on. And I think it's a normal situation as you normally used in the energy system models. What is, oh, I missed a little bit. So what are the modeling effects, especially in the energy system modeling related to regional aggregation? Yeah, without any regional aggregation in the energy system, you more or less have a aggregated one-point model. This means that you have more or less a sector or consumer homogenic. You have no differentiation between numbers of technology systems. There are only one group or in one place, especially if you look to the capacities and the activities, they will be aggregated. And in the other sense, for example, you don't have really a decentral, you have more centralized worlds due to the fact that if you, for example, modeling storages, they will be more or less aggregated to one big storage for the whole system. And due to this effect, especially if you look to the supply and consumption situation, yeah, simultaneous effects will be neglected. And at the end, due to this aggregation process, you have more or less an overestimation of potentials, especially of the potential of storages, especially also if you look to the autarky or something like this. And the assumed total costs for storages or for distribution energies are much lower as you normally have in reality. And you also not be able to modeling individual actors. So you have in the model really synergies that which do not exist in reality when you use this model. Related to time resolution, I think a general point is by aggregation of time steps, the time discrepancy between generation and demand is reduced or even neglected. I think it's clear if you look to on the 1 year level, if you look what is the possibility or the possibility to have electricity by photovoltaic, and you look at only by a year level, you more or less have only the aggregated balance of supply and demand. The consequences on this side is also that you have normally the storage requirements are underestimated, and also something like storage losses, self-consumption, and so on are not really taking into account this. It means on the other side, I think if you look again to this, you have the problem that you have to find a compromise between accuracy and the model size, with regard to the temporal and resolution in the regional aggregation, which is at the end necessary. So is a question, or you can ask yourself the question, should I model as much as possible regions, and should I include as much as possible time slices? And the approach we are normally using is, we have had also in the past, or we are using models with more regions, but if you're going to the local level, we assume that it's necessary that you are splitting up the model in typical supply and demand situations. And for this typical supply and demand situations, what we are doing therefore is we are make a simulation before, and with this simulation or with this modeling, we want to calculate the framework conditions of the different typical supply and demand situation. We want to find limited values or behavior patterns from the simulation, which we take into account. This means that we don't explicitly model anymore the regions. We are more focusing on the simulation of typical supply and demand situations to take into account prosumers or prosumers behavior. And this approach and this takes into account that the different model actors have different boundaries, have different effects, and have different considerations to the balance area. And with this approach, we avoid that the model assumption is going on only perfect competition. It's more going in the situation that we have modeled also, or taking into account something like soft barriers between the sectors, the actors, and have so also into account that there's or might be a slower down of the transition. For example, with electric mobility, what we are doing is we are looking what are the weekly profiles for slow charging, the person kilometers, vehicles availabilities, making their then with the times an analysis of the load peaks, the energy current imports, and the PV use. And this means that we are implementing such prosumer behaviors by a decoupling of the charging style, storage, and use of the electric vehicles. This means that we have, on the one hand side, a charging process where we are simulating before what is the possibility of charging, what is based on such a simulation approach. We include storage processes where we're taking into account that the availability is not every time there, and where we have also this distribution process where we say, okay, there's a possibility of a tube for charging of and say, therefore, for example, if you're using the times model, this by a flow fraction with an upper and lower time, to taking into account that there's a possibility to charge, and at the end, the model decide in which parts it's loading on. What you see here is, again, that we have a time resolution, and come later on to this. And so what I say with to the regional aggregation, we are subsidizing the regional aggregation and taking into account, instead of the different regions, more and more this prosumers or demand and supply situations. For the time resolution, I think it's clear you have this model horizons, you have the possibility to split it up in the year and seasons, typical weeks. And for these typical weeks, what we're taking is therefore, we normally take such typical weeks in hourly time resolution. And this is due to the fact that what's here, the slides lower on shows that with the increasing aggregation, you more and more have a storage effects. And this is the reason why we are going to this typical weeks. But we have there also a speciality. The speciality was, as I shown before, you normally split up the year in the 4 seasons. And what we are doing is we are saying, okay, normally you have the effect that there are some special situation if, for example, modeling the fluctuating renewable sources. In this case, that under these circumstances, you have a special supply and demand situation, and therefore we are modeling the additional week. In this case, we call it fall week, to take into account that there might be a special situation between supply and demand. This is more or less a short presentation of time resolution and regional resolution you take. Thank you for your attention and thank you for listening to me.
Thank you very much, Marcus. So I'm keen for anybody to make any points that they want to make, or if they have any questions. Can we start off with any questions of clarification about what Marcus said? I mean, maybe as a starting question, Marcus, can I ask you what sort of temporal resolutions you've tried in your model? And what sort of spatial resolutions? So what's the maximum you would ever go to and why, for example, for each? And how do you decide what is appropriate?
So the maximum we have had used was for on this local level was more or less 4,000 or over 4,000 time slices. So in general it works, but I think the problem was the interpretation, and the other thing is you normally have to really find this for this time resolution, the demand and supply situations, and therefore I think with a normally grid modeling, you make some approximations, and for example, if you're looking for a settlement, then the settlement is more or less aggregate sum of different buildings, and if you put, for example, for each building a demand curve for heat, then what's in reality happens that you have a stochastic variation of these curves, and so at the end your model might be exact related to the different buildings, but it's not exact what you observe in reality if you sum up these buildings. And so this was also the reason, for example, why we reduced this time resolution to this typical weeks, and including additional this week with to match or to model the special situation.
Okay, that's interesting. And have you done any thinking about whether, when you choose the time slices, would you base them more on what's happening on the demand side, so variations in demand during the year, or maybe on the supply side, variations in renewable outputs? Or do you need to consider both?
Maybe we have thought about both things. We have thought on the one hand side on the demand side and on the supply side, and I think, for example, what we have included inside this also was, we have also, for example, included or start with this seasonal storages with this approach. And therefore, what we've done is there, okay, if you look into the model approach, you have normally solar thermal, heat pumps, electric resistance, and you have there this seasonal storages. And for the seasonal storage, we have modeled it in this way that we say, okay, you have on the one side and the storage in process. We put the storage inside process, for example, on the weekly level, and the storage as self on the seasonal level, and the out again wieder on the weekly level. And therefore, you have also this reaction related, for example, here seasonal storages. And so what you see here is normally, I think this the seasonal storages are the complete, or one example, therefore, that you're coupling really on the one hand side the supply side, on the other side the demand side. And so this was what I had also tried to say before. The difficulties related to the time resolution is that you really find for all situations, for all supply situations, for all demand side situation, the load duration curves or the load curves. And in the other point, if you, for example, take not the fully load curve, that you're also taking, also that you find the relation between the supply and demand situation. And therefore, I think the experience, also it was a long time that we start with this experience, is that we decide that the best thing for us and was to take the time resolution for typical weeks, to make it there for each of these weeks on hourly level, and for the dimension or yes, the capacity design and the extreme situations to include one special week.
Okay, it's interesting because it's a quite different approach to what we've taken in the past. There's a few questions on the chat that I'd like to go to, Marcus. I don't know who some of the names are. So the first question is, or I don't know who the people are who are asking the questions from their names in some cases, from God only, it looks like. The first question is, in the slide showing EV and battery decoupling, why are you modeling one battery process for each hour of the day?
So this was the reason that we want to take into account that if you, for example, starting a charging process, that you then, yeah, that this is then a decision. And on the other side, we want to really to have the possibility to implement the simulation process, that it's not possible for each group, for each member to load every hour. This was more or less to model or taking into account the behavior of the prosumers.
Okay, thank you. And how are the vehicle to grid and the grid to vehicle time slices matched with the hourly mobility demand?
So I think it's necessary to, this was what I tried to say is it's necessary to distinguish. On the one hand side, you have the hourly electromobility demand, the person's kilometers. And on the other side, the question is when you'll be able to charge the vehicle. And this was the reason why we distinguish there between the two processes and make this with the flow fractions especially to say what is the maximum charging rate and yeah, how it depends on, because if you're not taking into account such especially things, it might be happened in an optimization model that you are yeah, decharging and charging at the same time.
Okay. Antonio has a similar question and asks if we could go back to the vehicle to grid slide, and if you could just say a few words about exactly how you modeled vehicle to grid.
So the vehicle to grid is it's going in the same direction as we have this with the flow fraction, that we say in this time, when is it possible to that we add yeah, or when we have this charging strategy back, and so it's also modeled in this way, like a distribution process with a definition of this flow fraction.
Okay, thank you. And Manuel asks, is transport demand also given hourly in person kilometers?
So the transport demand is also given in hourly. So yeah, what I haven't included in my presentation was what I tried to say with this approach before, is that we really have to start a simulation over 1 year, and that based on this simulation of 1 year, we are identified when and under which circumstances during, or what is a typical week for the season from the vehicle demand of the person kilometer demands, and on the other side we are simulating when there's a possibility of charging or not charging of the cars. And this was what I tried to say in the first step. We have developed for all the typical demand and supply situations simulation models, simulation models in hourly basis for the whole year or more, and then aggregated or analyzes this results also to include it then in the model. And so with this simulation approach, you have also the possibility to give restrictions to the model, that the charging is not the charging in the matter of a perfect competition or a perfect system action. So you can taking into account that people have some requirements related to the battery charging. Might be that the people are only happy if the battery is half loaded. So that you don't have the full flexibility to use the battery. And this is, for example, something if you have a simulation approach, you can simulate it and find the parameters to restrict the use of the or the batteries. And in the second step, you have then this kind of prosumers inside your model.
Okay, thank you. I've got one more final question on the chat for you, Marcus, and then I think we need to move on to Tom and Evangelos. So this is from Vahid. Are there any specific conclusions in terms of the minimum required level of subregions spatially that you thought were appropriate for your model, and why?
So what I haven't explicitly said is, so in general, I think it's not necessary to, you have one region, and in one region, you can distinguish by different process or supply sectors or supply situations. And by making this distinguish, you might have also something like modeling a different region. And so I think at the end, the region is not the question. The question is what or how many different consumer or consumer supply situations might be useful, might be necessary to model the reality. And I think it's something different related to regions or the number of regions. If you really want to model something like grid investments, that you want to show how far or what is the cost to extend, for example, an hydrogen grid on a district heating grid, and then it might be necessary or much more useful additional to include this region, especially from the perspective of to model it much faster because of this similar situations in some regions. But I think grid issues is a special issue, and under other circumstances it's necessary to look carefully how many actors do you have and which are the actors from the supply and consumer side, and this might be also the representatives of the regions.
Okay, great. Thanks, Mark. It's really interesting how you try to deal with how technology demands vary in reality. I think we need to move on to the next talk. There is one more question in the chat, and maybe you could try and answer that in the chat if you have a chance. But I'd like to move on now to Tom and to Evangelos, who are going to talk about their experience in their model. They're both from PSI in Switzerland. Tom.
Yeah. So hello, everybody. This is Tom Kober speaking from the Paul Scherrer Institute. I will talk about global modeling and my experiences with increasing the spatial resolution of a global times model. And I will then hand over to Evangelos Panos, and he will be talking about increasing temporal resolution in times models. So very briefly, this doesn't work. My experience with increasing the spatial resolution of a global times model refers to my engagement at ECN before in the Netherlands. And there we expanded a TIA model, so a global times assessment model, a 15 region model to 21 regions and then 36 regions. This relates to specific projects. One project focusing on Latin America, where we expanded to 7 Latin American regions, the TMECN. And while Mexico, Colombia, Brazil, and Argentina were of particular interest in that project, we also detailed Venezuela and Chile as specific regions here, just due to the fact that Venezuela has an important role in exporting oil products. Chile is an IA member country, so there's also good data available, statistical data available, and also given to the fact that the energy structure in Chile is different with availability of natural gas resources compared to Argentina, for instance. So this refers a little bit to also what Marcus has said. So with a higher reach or spatial resolution, we want to contribute to the fact that different regions, or in Marcus' case, it was different supply/demand options are different. So the heterogeneity of the energy system. So, and then in a other project, we detailed the African region of the TIAM model, where we established 17 regions for Africa. Yeah, well, which actually was quite a challenge, but we came up with this composition of regions due to various reasons. We were aware that the North African countries have a very special role in exporting natural gas, in the availability of wind, in particular in Morocco, PV in Egypt, also wind in Egypt. So, and we wanted to have this separated, these different resource availabilities. And then, of course, we did also consider that South Africa is a front runner on the continent in terms of the deployment of the electricity grid or the electricity system in general. So it was clear South Africa needs to be a separate region. And then the regions in Africa are quite heterogeneous with regards to the resource availability. So for instance, also Kenya, which you have in the eastern part of Africa, is endorsed with quite substantial geothermal resources. Ethiopia has a lot of hydro resources. Congo has abundant hydro resources, and the South African region has a lot of coal. So this, in the end, motivated us to come up with 17 regions for Africa, contributing to the different development status of the regions, but also due to the fact that we have different resources. And implementing this higher temporal resolution for these two continents, well, was quite a challenge in terms of the data source management, I have to say. Of course, the IEA energy balances as a kind of a default had to be taken into consideration, and also the national statistics. And there were plenty of other resources which we have used to quantify the status quo and future development perspectives of the respective regions of our TIAM model back then. And actually, due to the fact that we had so many different data sources involved in this, I developed a separate, very comprehensive database which collected the national statistical sources, converted this into the regions which we have defined, and that then fed directly into the respective weather input files. And so that was a challenge in terms of also just the data processing, getting the right region mapping, because we do have different source data involved. And I mean, you are all aware of the region mapping which you do for the, for instance, reporting to the IPCC databases. But then you can do, or you can expand this kind of region mapping to all the other global modeling databases, which can be very well incorporated into a higher temporal resolution of a global model. So this was a major effort here. And I also dealt with a kind of a restructuring of the TIAM model to be able to incorporate much better these central data sources. So I tried to separate to some extent the structural part of the model and the region-specific data. That means in the base year template, I only tried to keep in the energy balance data for the base year, and then all the other data which characterizes a specific region. And now here we talk about 36 regions for the whole world, have moved to scenario files. And this was very handy because this allowed a much more streamlined data processing from this central database to the weather input files. And what I also, where I invested quite a lot of time, and this was also a learning process for me, is I restructured these scenario files, or in general, the weather input files, that they had a very quite let's say, a common structure, which made the links to the database much easier. Also for convenience, I reconstructed this demand projection file as a scenario file, and specifically for the African regions, I modified a lot these different demands of the African regions, and this I did outside of FedUp, just with the Excel calculation file, which I incorporated here. So this higher resolution or higher spatial resolution of the TIA model ultimately also enabled a GIS-based electricity access analysis for Africa. This work has been led by my former colleague Francesco Dallalonga and also Bob van der Zwaan. And here they incorporated information from a geographical information system, which identified the costs of expanding the grid and the resources which are available to us in the vicinity of a certain settlement, or how the costs are for mini grids or for off-grid solutions. I have given you at the bottom here the respective links to the publication. And this kind of GIS-based analysis was only possible with a higher spatial resolution of Africa here in that case, and by incorporating the heterogeneity of the different African regions with respect to resource availability, with respect to infrastructure, and the development of these regions. So I think now I will hand over to Evangelos. Evangelos will elaborate on the temporal resolution times modeling.
Thank you, Tom. I will try to be short in the last 5 minutes that we have. Although my presentation is not so clean, I apologize for that. So next slide, please, Tom. Okay, thank you. So I will start with a fundamental observation that also Marcus said, that low intra-annual resolution can lead to underestimation of flexibility needs, overestimation of renewable penetration, and underestimation of renewable energy sources system integration cost. And I'm presenting here a first paper from Canan, from my colleague Canan. This work led to, inspired, I would say, the development of the Swiss Times energy systems model. And there it is based on an electricity sector Swiss model. And Canan tested two hypotheses here, one hypothesis with 288 time slices and one hypothesis with 8 time slices. And what it has been found here is that by having a coarser deterministic model, then we have an issue on capturing the variability of renewable energy, the needs of flexibility, and the overall integration cost. So as you see here, the system cost in hypothesis with 200 time slices is much higher than the system cost with the hypothesis with the lower time slices. And also, as you can see on the electricity generation profiles, we miss the deployment of flexible capacities to cope with the integration of renewables. So next slide, please, Tom. But this, and here I'm borrowing a work from Paul that he was so kind to provide me for the presentation for the storage with the collaboration that we have with the TCP. This depends, however, depends on how the time slices are chosen and what is the model structure. So it's not always straightforward by that when one increases the time slices, it gets, let's say, more deployment of storages, or for example, a higher system integration cost. And here is 2 examples from Paul with the UK Times model. with 6, 16, and 192 time slices. And you see in the yellow table the deployment of storage, which doesn't increase significantly above a threshold. And also on the table below the yellow table, you see the objective function that varies only slightly. So this inspired, next slide, Tom, inspired a larger work on the BIMI project, where we took advantage of high performance computing to examine very large instances and to find a sweet spot on how many time slices we need. And the first approach that I'm presenting here is just a straightforward averaging of the load curve, the demand load curve, the electricity load curve. And we average it into 288 time slices for 4 seasons, 4 days per season, and 24 hours per day, 672 time slices, and 2016 time slices. And of course, the solution time, as you can see in the chart on the left, is exponential with the time of with the number of time slices, while the solution accuracy, as you can see on the chart on the right, does not improve after a certain number of time slices. And with this model here, the sweet spot was found that it doesn't make any sense to go beyond 672 time slices. As you see, the 672 time slices and 2016 time slices almost give to very similar results. Next slide. But this depends on how the time slices have been selected. And before, it was based on simple averaging. But if a more clever approach is used, and we are using here representative days based on the tool from Crispon-Sellet, which is available on ETSAP, and it can be downloaded, one can select a number of representative days by minimizing the difference between the actual load curve and the approximated load curve. And as you can see on the chart on the left, you can see that with 288 time slices, which is 4 seasons, 3 days per season, 24 hours per day, the approximation of the actual load curve is much better when representative days are used compared to the averaging of time slices. And as you can see on the chart on the right, the orange values represent to the representative day selection, while the darker values represent to the averaging time slices. And we can see here that with 288 time slices selected with the representative days, we approximate the solution accuracy obtained by 672 time slices, which have been selected by averaging. Next slide, Tom. And so this leads also to other approaches that it is not always necessary to go to tremendous number of time slices, but we can be a little bit more innovative on how we select them. And here I'm presenting a paper from Pernille Selsom from Norway. She has also provided this to me for the storage collaboration. So here, instead of using a deterministic model like before, we're going to a stochastic approach. And what is presented here on the left-hand side is a two-stage stochastic tree, where in the first stage, the model is solved, takes only the investment decisions, and in the second stage, the operational uncertainty, which depends on the wind and solar variability, is revealed to the model. So in the second stage, the capacities are fixed to the solutions of the first stage. And then the model needs to hedge on that. And as you can see on the chart on the right-hand side, you can see that the stochastic model with 48 time slices, which is around the middle, which is on chart C, around the middle, as you see there is a stochastic model with 48 time slices, has the same approximation as a deterministic model with 672 time slices. And this is way far more computational efficient. And next slide, Tom. And a second approach, which also leads to what, which also correlates to what Marcus has presented, is the non-symmetric time slices. And in this approach, what we can do is that we put emphasis on a particular day, or it can be a number of days, it can be also a week, with a higher number of time slices, while all the other seasons and days are having a more coarser time slice resolution. And in this is from the Japan times model from Shiroshi and Amit. We can see here that with 56 time slices, and daily hourly resolution is captured. And then this approach can be suitable for modeling critical days and critical hours. So next slide, please, Tom. So these are the conclusions, that the straightforward increase of resolution via averaging is easy to implement, but does not eliminate the smoothing in various output. And this means that beyond the level, you reach a point where the overhead that you get in the solution time doesn't pay back. A straightforward selection of representative days using the classic clustering techniques loses the chronology. The tool from Crispon Select is a good, I find it as a good approximation and a good compromise, and allows sampling joint probability distributions, and you maintain also chronology. And if you want, I can show you an example of how I use this tool. I have it in a backup. And the stochastic programming helps in capturing the variability. It can be computationally efficient if the probabilities in the scenario tree are carefully chosen. Non-symmetric time slices are also computationally efficient. They should be carefully selected to avoid decision based on extreme cases. So it's suitable for examining robust solution, I would say. And here I would like also to point that capturing the variability of renewables is not only done by increasing the time slices, but we have also in times other mechanisms, like the implementation of residual load curves, introduction of dispatching constraints, and implementation of ancillary services, which all these topics, if I'm not mistaken, will be parts of next series in web seminars of ETSAP. So that's all. Thank you very much.
Thank you very much, Tom and Evangelos. That's great. Really, really interesting. Can I ask a quick question of clarification before we take points from other people, which is on your use of Crispon Select's tool. And I think you used both the load curve and the and intermittent generation in that tool. So you looked at wind, solar, and the load curve. So you had quite a few different variables there that you considered. Certainly, when I did it, I only considered the variable renewable generation. I didn't consider the load curve, we did that because it wasn't clear that there would be any correlation between load curve and variable renewable generation. So is it worth mentioning for a minute why you used both and what you found? Because I think this seems to have had a much bigger impact than what we found when we only considered variable renewables.
Okay, Paul, thanks. No, actually, I based that on the load curve, only on the demand load curve, not also on solar PV and wind availability. But if, Tom, you can go 2 slides further. Yeah, here. I don't know how much is visible here, but on the left-hand side, the thing that I did, because that was a European model, I took the different load curves of the different countries, and I put a weight on them, because the tool allows weighting the different load curves. So I put the highest weight for the total of Europe, and then I weighted the different countries based on their, let's say, contribution to the total demand. So no, I didn't put also the wind and solar in that selection. It was too complicated, and the tool took a lot of time to converge.
Okay, thank you. That's really interesting, because it's one of the questions I've had. One of the outstanding questions is what the better approach is. Should you worry about the renewable side or the load side?
It was on the demand side, because it's a mixed integer programming, and then it takes a lot of time sometimes to be solved. So yeah, this is the drawback of this approach. But also you had experience with this tool, right?
Yeah. There's a question on the chat from Antonio. How did the computational load increase with the application of stochastic approaches? And how different was it from using non-symmetric time slices computationally?
I think for that we need, I will point you to these papers from Pernil. Pernil says, I don't have it here, but in the publications there is a chart which indicates how much time she needed to solve the stochastic model. Yeah, it's very difficult to compare the two approaches because I haven't compared them on the same model. So this is something that needs to be done. So these are different models, so I cannot answer this question.
There's a question from Etsushi. How does the selected time slice accommodate the dark doldrums? I'm not sure exactly what the dark doldrums are. Maybe Etsushi, you would like to unmute yourself and explain what you mean exactly by that, if you can. Well, I'll tell you what, we'll come back to that question. Sorry. There's a comment in the chat. So Etsushi says, for periods where you have a long period with low wind and solar output, how did you cope with that in the model?
This is very interesting question. I'm not muted. Okay. Obviously, when we are doing representative days, it can be that we lose this option. I would suggest here that an approach on non-symmetric time slices or a stochastic approach can perhaps be more suitable for assessing these types of events. And of course, if one uses the stochastic approach, we'll need to assign a probability on putting zero availability of wind and solar on these particular hours. With representative days, you can do that if you have a historical period from where you can select only for this part of the historical period which this effect is occurs, but I wouldn't recommend this approach for this particular extreme event.
Okay, thank you. And a question from James Glynn. Is sub-hourly time slice resolution dispatch modeling mathematically possible with the time source code? So dispatch modeling. So he's interested in dispatch modeling and whether you can do sub-hourly time slice resolution for it. I mean, I guess
Antti has replied that it is possible. Thank you, Antti.
I guess it's getting into balancing issues and into the ancillary type markets, and so it's how you cope with those. Okay. I don't know if we have any more questions on the chat. I don't think. I'm interested in how you actually set up the times model practically. So supposing you do want to try different temporal resolutions, presumably you want to design your model so you don't need to redesign the whole thing in one go when you do that. So how do you design the model to be flexible for temporal resolution and maybe even for spatial resolution? What steps do you take?
Yes. We started, that was made from a colleague of mine, Hassan Ayman, who is not with us anymore, but he did a great job on that. So we started with the lowest resolution possible. So we started from 8,760 time slices, and then we started aggregating. How we structured the model, it was that we had different DINS tables for the time slice dependent data. and different tables for the non-time slice dependent data. And then we had also different C settings files, but I don't know if I am answering the question now. So we had different scenarios. I don't have that in my computer to show. It was in my previous webinar when I went into that approach, how we designed that. But we had different scenario files, a scenario file with 200, a scenario file with 2000, with 8000, with 4000. All the load curves were in these scenario files. The commodity fractions were in these scenario files. Everything was in a scenario file, which was selected. And the C setting file needed to be changed because the time slice definition should have been different. So we kept 4 different versions of C settings files and 4 different versions of time slice dependent data.
Okay.
Not very clever, but.
Well, we did a similar approach on UK Times. So we had different sys settings files for different numbers of time slices, and the basic model was designed as an annual only model, which also means that it solves really quickly and doesn't produce a huge amount of output. So it's great for developing the model itself. We developed it.
Exactly. It needs DINs. Without DINs, it doesn't go. It's very, takes a lot of time.
Yeah.
And I think to your question, Paul, I mean, I think it's rather easier to make it more the times model more flexible with regard to the temporal resolution, but not with regard to the spatial resolution. I would abstain from making a spatial flexible model where you can expand and collapse regions with a tool. I saw particular problems when you have market shares and share user constraints included. It's from my perspective, it's a huge effort to recalculate everything that you have reasonable trajectories of whatever side constraints you have in the model. And I think you also had some attempts for the global TR model at UCL, right? To be more flexible with regard to the regional representation, right? And
we've been thinking about it, but we haven't actually done it in practice.
Okay.
And I'm still keen to see how many scars other people have when they tried.
Okay.
So related to the time resolution, what we have also developed or what we have used was, we called it Flex tool, where we automatically changed the Excel files for times, means the demand profiles and the time slices in these Excel files. And what we used is what Evangelos presented before, also the tool from Vito, to define at the end the signification of the load curves. And based on this, in this combination, we calculated on one side, based on the number of time resolution we want to have inside the model, automatically on the one side the load curve, and on the other side we make automatically the changes in the Excels, that we have more time slices, and the duration of the time slices then automatically will be defined. But I think the problem starts if you have much more demand categories, and especially if you want to take into account uncertainties. And I think what we try to do is we try to analyze how big is a mistake if we have less time slices or more time slices, and we don't find really a good answer to this. I think we only find that it's very often depends on the supply and demand situation you are looking for.
Okay, that's great. Thanks, Marcus. I think we'll have to call it to a halt now. We're after 1 o'clock. Thank you very much to Marcus and to Tom and to Evangelos for their great presentations and their comments today. I think it's been really interesting, fascinating how we do things. For the next webinar, the next ETSAP webinar which we're planning for March. It doesn't have a date yet, but an advert will be sent out. We're planning to continue the high resolution modeling theme, but to particularly focus on variable renewables. So again, I think we'll have two presentations, probably one looking at hourly representation and dispatch and unit commitment options, and the other one looking at stochastic approaches. So there will be an email out about them. So thank you very much to all for attending, and we'll see you next month.
Thank you. Bye-bye.